Thank you. So hello, my name is Gerhard Dorn. I'm senior scientist at Virtual Vehicle, which is a research company in Austria dealing a lot with mobility, rail, and also autonomous driving. And I work in a project called AI for CSM. It's a European project, and we are working on a prototype, a robotaxi. And this is the car. This is our Ford Mondeo, which has the possibility to drive it by wire, so we can really do autonomous driving. And I work in the perception task. And what we have on top is a LIDAR sensor, which is a very cool sensor to get data about your environment, and I will show you how that works and what the challenge, for me at least, is to process all this data in real time in the car. And the connection is I'm using Julia for that. When I started at the company, they all used, I don't know, C++ and other directly CUDA implementation, and I just didn't want to use that, and they were not so approached or not so well established. So I had the chance just to work in Julia, and that's a bit my story, how I integrated that with the other colleagues. And yeah, and we just use a normal PC, so it's not embedded at the moment. This is also maybe interesting, but yeah. So this is a common LiDAR sensor. This is the OS2 Auster, which gives you 2.6 million 3D points per second, and we want to process that in real time. So it's really amazing what this sensor can do. It also gives you the reflection, so the intensity. You already can read the lane markings and everything. You see the signs, so you can also recognize graffiti on a wall. It's a really very powerful sensor, and I would say still expensive, but in the advantage of laser technology, I think, and also semiconductor processing, I think it will go down by some factors, and then it would be very interesting to have them in cars or as roadside units at streets. And so the challenge is to process this 2.6 million data points, and what we also do is we have a digital twin in Unreal Engine. There is a driving simulator called Kala, which is basically open source. This is like the car which we simulate. Then you see the 3D point cloud simulated in this simulation tool. Then on the right-hand side is one thing which I'm working on, an occupancy grid, which tells you where's free space and where is obstacles, and there was the intelligence. That's another video where we overtake and simulate overtake maneuver of a bicycle. So on the left-hand side, there's the intelligence module, which has a state machine and which is handling, can I take over, does path planning, all that stuff. I'm more interested in the right upper image, which is a semantic segmentation. So I get the LiDAR points, and I want to classify, is this LiDAR point a ground point or is it a wall? So basically ground segmentation. And I would do that with machine learning, with Julia, in the car, in real time, on a GPU. And on the right-hand side and below, you see the occupancy grid. So I use the data to get just a map where's free space and where's a wall. And these are the two challenges I have in perception. So the left image again is, I have 5 classes, so I also want to detect objects, which is not working that well, as you can see from the left image. And the ground is a mixture of street and terrain, which is basically the same in this simulator because everything is flat and you don't have really features to discriminate between them. But yeah, that's okay. So this is the challenge. I also have some slide about what the occupancy grid is, if you're interested in it. I just have to look at the time. So if you have a car and it has LiDAR points and you really get the 3D distance of this LiDAR point, and then I can say, okay, if I hit a cell, I say it's occupied. And all the other cells which I just passed through are free. This is blue. And the interesting thing is, what if I move further and do another LiDAR measurement? And I have again points. And then what can happen? Okay, some cells can be passed through which were obstacle before. So there are some cells which I gave the color blue and red. Some cells are now red which have been free before, which is this one. So maybe there's an object which is moving here. And so you can take this information to make also estimations about dynamics. And so this is t plus 1. And you see in the right-left corner, there is maybe an obstacle which came closer, because first it really passed through the cell and then it came closer. And yeah, what you can infer, maybe there is a wall, maybe this is a new object which was not here before, maybe this is a car moving away, and maybe this is a car moving beyond you. So this is the the data structure, also the idea to work with time steps, maybe do a convolution also over time to get these features and to infer on where objects moving. So this is the occupancy grid, which is basically fill in 3D points into a grid and then also check which cells did you pass using Brazenham algorithm and using some probability theory. So this is not so involved. And this could be a logic. 2 times 3 is 3, and 3 and then occupied. Okay, something is moving in or something is moving out. This is just the very basic heuristics how you could describe use this. And how do I do the semantic segmentation? So this is a 3D point cloud, and on top you see a spherical projection. So I have, I use at the x-axis the angle around, so it's a 360-degree view, and I have some vertical angle, and I just map each point into a spherical angle. So this is, then you get a 2D picture, and this is what I get, for example, from Carla. You see this is the 360 degree, this is in front. Here you can see the bike in front, and this is just the vertical angle. And you get also different properties which you can calculate. So this is basically what is the angle change if you look up and down, what is the angle change if you look left and right, and you can use this as inputs for a machine learning network, which I use. I use Flux with UNet. So UNet is basically a classical image segmentation program, which for me it was easy to implement. So you have to do some convolution layer, you have to do some skip connection. So this is basically, I do some convolutions, and then I copy this array to the left-hand side to reconstruct the original one. And here I go down, go down, go down. Here I define features. I go up, up, up again, and I want to, I say here, maybe I have 10 features, the 10 classes, and I want to say which pixels belong to those 10 classes, and that's why I have the skip connections where I can reconstruct in the full image space. So this is a standard algorithm. There are better algorithms, but what's the challenge for autonomous driving is you want to have not the best in precision, but a real-time capable algorithm. So something simple which is good enough. Okay, and here's the strategy. I put everything together, so it was quite nice to start prototyping in Julia. So this is, and okay, this is not a pipeline. So in the car we have, I said drive-by-wire, so we can control the steering angle, we can control the acceleration, and this basically works over a CAN bus, and you have to do some sensor and actuator control, and we use there is a classical program called ROS, Robot Operating System, and then there is an alternative for this, which is RT-Maps, which is real-time multi-sensor application, something like that. We use that because it's rather simple. You can have blocks. This is the where's the mouse? This is the LIDAR input. This 2 GPS inputs, and the important thing here I have a Python bridge, so I don't have to actually use C++, and here is Julia inside. So this is the maybe weird way how I implement Julia in the car, because this setup was already there and my colleagues wanted to work with RT-Maps. And then, okay, there is a Python bridge. Okay, I integrate Julia with JuliaCon. And okay, I work on a GPU inside. And it works. So this is cool, and yeah. And so I also experienced with the other package, what was it called? So there's Python call and PyCall, and not Julia call, but Julia. Those are the older versions, and the new one's a bit more stable, I would say, and yeah, it works. There's some things if you want to do parallel computing, which are maybe a bit tricky. So how fast is it? This is just the benchmarks from the semantic segmentation in the computer, which we will use in the car, and they are still too slow, so about 250 milliseconds, and it should be below 100 milliseconds. And the occupancy grid stuff is below 150 milliseconds and should also be faster. And if I run everything together and measure the time, it's about 1 second, and this is factored 10 times too slow. But I already had some mentoring session with Julian, who showed me how to debug the GPU. There's CUDA.profile, and you can watch how many time do you lose for which step, and maybe there is also a bug. And the problem, he said, is if you do too many allocations, it costs you time. So this is the next step for me. Also learning a lot here at JuliaCon, how to improve my code. So what I did so far is I prototyped, I integrated, and now I make it fast. this is the strategy. Yeah, how to make it fast. I work at the moment at 10 Hertz with the full resolution of the sensor, but I can just delete points. I don't need all the points. I don't need points which are behind of me. They're not so interesting. And I wanted to show you how it looks like at the moment. 1 minute, yeah. This is, where's the car? There's the car. So this is a real-time measurement somewhere in Graz in Austria. The car is moving, you see the point clouds. Here you can see also the reflection, which I have to show that, which is super cool, so you can get an impression of the sensor. And you see quite a lot. You can see the line markings, you can see the zebra crossings. This is just because they reflect more, and yeah, the rotation doesn't work that well. And this is the occupancy grid, which I need to improve from a velocity perspective, but you can see the free space and the occupied space. And yeah, basically that's what I wanted to show you. If you have any question, just contact me. And if, yeah, thank you.
Thank you.